Okay, so in this video lesson, we are going to look at an example to see how we can compare two population mean values. And so let's spend some time reading the description of the problem here. And I apologize for the sketchy description of the example, but it will get better as it's being explained along the way. And so in this example, we are studying about the engineering certifying exam mean score. So any university nationwide here that has an engineering department will offer a what's so-called an engineering certifying exam. That's an exam before engineering students can become formally certified into the major. And so here in this problem, let's say we have two universities. One of them is Newton University, and the other university is Gauss University. And so engineering certifying exam mean score is what we are studying here. And so from Newton University, we found a sample according to the way how the wording is describing here. Then from Newton University, we found a mean value, a mean of 85.5, and these scores are supposedly out of 100. So the mean score from Newton University is 85.5 with a standard deviation of 6.5, where and all these information is from 450 scores that are randomly selected. And so that's the highlighted information. And then the same certifying exam right there, but now when we're looking at the Gauss University students, then we've found the following sampling information. From Gauss University, we found a mean of 80 with standard deviation 5 in a sample of 400 scores that are randomly selected. And so in this example, as a continuation from our general discussion from our general lecture about comparing two population means, then we can draw out some given information as following. The first thing, as I have explained back in the general discussion or the general lecture, is that the main population mean value that we are studying here is the engineering certifying exam mean score. So this is a population mean because really, as I have already introduced earlier, this engineering certifying exam is not only offered at Newton University, it's not only offered at Gauss University, it is offered at any university in the nation as long as there is an engineering department. So this, in other words, this mean score here deserves its place to be a population mean because there are a lot of students in the engineering field. And so now, when we are particularly studying and comparing this mean score from the two schools, one of them is Newton University and the other one is Gauss University, then we are in a situation where we're now gonna break it down to two separate populations. So Newton University is one of them, Newton University, and from Gauss University. And so clearly there are two populations that we would like to compare the respective mean value for. And so just like the idea that I have explained in the general lecture, then now once we realize that we're working on two separate populations, we're trying to compare their respective, we're trying to compare their mean value here respectively from these two different populations. then it is extremely convenient that we are giving a numerical label for each of our population here. And so I can now label this population 1. So it's not really because I favor Newton University over Gauss University, but simply because maybe in my own, and it's just a choice, as I have explained so many times back in the general lecture. So here it's only a choice, and simply for me, I made this choice because back in the wording of the example itself, it makes sense that because Newton University was listed first, so I'll just go with that order like that. And so in this way, Gauss University as a population, or Gauss engineering department the engineering department at Gauss University is considered is labeled as population number 2. And so now that means we can regard to this as population 1. And this is population 2. And so now, once the numerical labels were given, then doing that produces the following importance right here. This same mean value, the engineering certifying exam mean score, but now if we're looking for that in population 1, then we are going to call that mu1. And so the subscript 1 here is indicating that this mean is to be calculated. This population mean is the population mean from population 1. Whereas that same mean, but if being found in population 2, we call that mu2. And yes, sigma for population 1 is also labeled as sigma 1, and sigma for population number 2 is labeled as sigma 2. So these are the parameters, the population parameters respectively for on each of our population here. And when it's now time to list down our sampling information, then from population 1, again back on the wording of the example, we have collected a sample of 450 scores randomly selected from Newton University. So this is now population 1. And so pay close attention to the mean and the standard deviation here before I switch back to the writing board here. And so now on the writing board, sample size that I use to collect samples on population 1, now I name that N1. This is 450. The sample mean that I have already found here, that I have already had in hand, that's x bar 1. And this is 85.5. And further, in this sample that we selected from population 1, then we also had a sample standard deviation. And since being from population 1, I give that subscript 1. So S1 here is 6.5. So this is sample standard deviation of the sample that came from population 1. And so now if we're looking over to population 2, the sample that we used, the sample size that we used on each sample from population 2 is 400, according to what's written in the wording description. And so now in 400 scores randomly selected from Gauss University, which is now population 2. And then this mean here is a sample mean value that's from population 2, and this is a sample standard deviation from population 2. And so that means now on this chart right here, on this table, I have x bar 2 equals 80, and S2 equals 5. And so now clearly in this example, just like how I explained back in the general discussion or the general lecture, then N1 and N2 need not be equal. And this is obviously one example out there. Exactly as a reason why N1 is chosen to be different from N2, there can be many different reasons. It could be that the student population from Newton University is a lot more than population from Gauss University, so we have more opportunity to pick a larger samples, whereas in a population 2 over here, at Gauss University, we have a smaller population, so it's only good enough for us to pick about a sample of 400 students. That could be one reason for leading to 2 different sample sizes for 2 independent samples here. And again, we are doing a problem where the samples are independent. And so here, N1, in this case, clearly not equal to N2. And that's obviously being shown in this particular problem here. And so immediately, once we have learned through the general discussion or the general lecture, then recall that a D, or the D value, is defined as the difference mu1 minus mu2. So in this case, it's going to be this value mu1 minus mu2, and it's always going to be a population value from population 1, subtract the value from population 2. That's how we define D. From the beginning here, the labeling, the numerical label from the beginning could have been the other way around. But the definition for D is always mu1 minus mu2. And we also define from the general lecture that a D bar here is simply a sample mean from population 1 minus a sample mean from population 2. So that's just some quick recall from the general lecture. And so immediately after looking back at this definition, then right here from our 2 samples, before I even get into reading the actual question of our problem here, then this is what we know about regarding our 2 samples together here. The 2 samples we've had, the 2 independent sample means we've had, produced for us a D bar value being, in this case, 85.5. This is a sample mean value from population 1. It's only one sample mean value from population 1. And we're subtracting 80. And this is a sample mean value that's from population 2. Our difference here, our current difference that we have in the 2 samples that we're currently having is 5.5 after calculation. So we already had a sampling difference of the 2 sample mean values that we're currently having. And recall further, throughout the example that I worked along with in a general lecture, that eventually in any of our work later, we're going to need to find the combined standard error of the 2 samples. So as a formula, as a quick reminder, it's S1 square over N1 plus S2 square over N2. And the entire expression is inside a square root. And so we can easily substitute in all of these values. S1 for 6.5 for S1, and 5 for S2, and N1 is being 450 here, and N2 is 400 for N2. But I have also developed a little program that's called the DF program that's being shown, that runs with Microsoft Excel as seen on the computer screen right here, that can quickly calculate all the values for us. And so I will come back to this to show how it runs again. So in this way that we will be sooner or later using a technology to calculate the value of the SEC. Let's for now hold on to its calculation. And so further recall that since we have 2 samples, we will need to find their overall degrees of freedom. And anyone viewing the lesson here in this particular video must have seen my explanation about the formula for the DF, for degrees of freedom of 2 samples, of 2 independent samples. And so we definitely need to use the DF program that I have developed to quickly find an answer instead of going through the very messy formula. And so now, back on my Microsoft Excel screen right here, S1 here is intended for the sample standard deviation 1. So here I am going to provide 6.5. I will put in 5 for S2, and I will put in 450 for N1, and I will put in 400 for N2. And so now this little portable program of mine now quickly calculated the SEC combined standard error for us, and it also calculated the degrees of freedom. And again, after my explanation from the general lecture that in a way how the degrees of freedom formula was given, which was also mentioned and described in the general lecture, then degrees of freedom here very likely to run into a decimal value like this. But then so for my class, to ensure that even students with very limited calculator capability can also work with the degrees of freedom, so I asked my own students in my class to use degrees of freedom rounded to the nearest whole value. And so in this case here, our degrees of freedom concluded to be 831. And so the SEC, as calculated from the Microsoft Excel screen earlier, was a 0.39546, and possibly a lot longer. But as I have mentioned before, unless being specified otherwise, usually SEC I'll round to 4 decimal places. So here we're going to use the SEC as 0.3955. So that's our value for SEC, and this is our degrees of freedom. And so this is now all of the given information that we need. First, I made a list of all the given information regarding the samples. And now quickly I calculated these values, because sooner or later a lot of our work will need these values, and they come right out from the sample. So this is what we can prepare ahead of time for us before we get into the actual question. All right, and so now back on the computer screen, now let's continue into reading the actual question of part A of our current example, because earlier we were only reading the general description of the samples that we've had, and these are the given information. Once they are given, they can be used for many different questions of an example. And so here the question is asking, according to the wording, at significance level alpha equals 0.001 are the samples, these two samples. And we have already sketched down the given information as well as some calculations from the two samples given here. So are the samples showing strong evidence that mean engineering certifying exam score of Gauss University is generally less than that of Newton University? So first thing that caught my attention here is that the question brought up a testing hypothesis problem. Are the samples showing strong evidence that, so now the comparison statements here that we're testing as a hypothesis is saying that we want to prove that the mean engineering certifying exam score of Gauss University, mean certifying exam score of Gauss University is generally less than that of Newton University. So according to the wording, mean engineering certifying exam score of Gauss University, as we're seeing again on the computer screen, mean engineering certifying exam score of Gauss University, that is, and right from the wording of the problem, that is mu 2, because currently we define based on our definition of with the numerical labeling, then the mu 2 is our population mean from population 2. And so now we want to show that generally mu 2 is less than mu 1, because that's what it said. That's what it said in the statements here. Mean engineering exam score of Gauss University is generally less than that of Newton University. That of Newton University means mu 1. And so now with this comparison inequality, we can algebraically rewrite this inequality as, in one way, mu 1 minus mu 2 being greater than 0. That's one way to algebraically rewrite this comparison inequality. Or we can also rewrite this inequality algebraically as mu2 minus mu1 to be less than 0. So we have two equivalent algebraic re-expression of this statement. And the point now, the purpose now, as explained in the general lecture, is that we want to rewrite any comparison statement as an inequality statement that involves a comparison between a difference and 0. And then we will choose this form right here because we have already agreed that D, the difference, is defined as mu1 minus mu2. And so now, after investigating carefully at the wording of the question, then now we can come up with our H1 alternative hypothesis. Now it's saying that we're trying to prove that D is greater than 0. Mu1 minus mu2 is a difference that's greater than 0, or simply D is greater than 0. And then from that, we can easily come up with H sub 0, now saying that D equals 0. Again, remind yourself that anytime that we have already recognized an H1, the alternative hypothesis, then H0 is going to be a lot easier to find out by simply rewriting the statements in H1, but replacing the inequality with the equal sign. And so now, in the way how this alternative hypothesis is saying, then this test right here that we're about to do must be a right tail test. And now that we know our testing hypothesis problem here is a right tail test, let's now carry out the steps here. So first step would be to calculate the SEC and the degrees of freedom. But since they're all listed and discussed earlier in the brief introduction of the problem, here I'm just simply going to rewrite and restate those values that we have found. So we have found D bar being 5.5. We have found and calculated SEC being 0.3955. And we have calculated earlier that degrees of freedom is 831. And so the point here is that if you're doing a problem on your own and we're not required to list down the information as I have made earlier, then we have to take the step calculating these values here formally. But here, since I already had those calculated and listed earlier, so I'm just simply rewriting them in one line here. After getting these values, especially the SEC and the degrees of freedom, the next step now is to calculate for ourselves the T star value of our sample. We can do that by taking the difference between our sample value, which is the sampling difference between the two sample means. We are going to subtract 0, the value that's stated in the null hypothesis, and we divide that by 0.3955. And again, as a reminder, calculating T star value is always done by taking the difference between our sample value, the D bar here, with 0, the value stated in the null hypothesis, and divide that difference by the SEC that we calculated previously. Calculation came out for T star of our sample to be positive 13.906. In this video lesson here, I have decided to use 3 decimal places for my T score, my T star value. However, for anyone doing the problem here, for anyone doing this kind of problem, make sure you watch for your own rounding requirements for each of the problems that you are doing. And so now, having T star being a positive T star, that we calculated here. The next step now is to calculate the p-value for our sample. And again, just like the explanation I have delivered thoroughly throughout my example 1 that you have seen previously, this t star is positive, together with the fact that our testing hypothesis problem here is a right-tail test. We are going to set up the p-value calculation as the calculation of the probability where we're going to find a sample value d bar being greater than or equal to 5.5 among infinitely many other d bar values. So again, I remind anyone watching this lesson that d bar that we have here is not the only value. There are infinitely many other values out there for d bar, being the difference between a sample mean from population 1 and a sample mean from population 2. And so now we can imagine that all d bar values that I have mentioned here can be placed on a bell curve, where center of this bell curve is at 0, and any value on this line is a value that we can possibly find for d bar. So our particular sample here, our particular value that we have in our sample, on this bell curve, it stays somewhere to the right-hand side of the bell curve center. So that's what d bar is. And so this probability calculation is the same as the calculation of how big this area shaded to the right-hand side of 5.5 on our bell curve. And then this d bar, from where it stands, has a t star equivalence, t star being 13.906, and it's a positive t star value. So now in order to calculate this area shaded to the right-hand side, we are now going to run our TCDF program from the calculator that we're using, the TI-83 or 84. So for anyone using a calculator other than the TI-83 or 84, there should be similar function that does the same work here. So now before I swing over to the TCDF program and show how it works right here, note how the interval that we're shading here has a lower end being 5.5, which is equivalent to this t-score, and an indefinite upper end, or in other words, no definite upper end. And TCDF program only runs on t-value. So now on your TI-83 or 84 calculator, we're going to call the TCDF program or command by accessing second variables, which will bring up all of the distribution functions in statistics. So now our TCDF command is found at this option right here, number 6. I'm going to hit enter to run that. Lower end, as we have discussed on the writing board earlier, lower end that the TCDF command is looking for here, we're going to type 13.906. So that's what we put in for lower end. Upper end is 1E99. So again, 1E99. We will input 831 for degrees of freedom. And now we're going to hit enter a few times. On a TI-83 calculator or some earlier TI-84 calculator, after calling TCDF command, you will notice that the command will be printed directly on your home screen. And this is where you will be entering your lower end and the upper end of the t interval manually. So 13, in our case here, 13.906 906 is what we enter for lower n, then a comma. Our upper end here is 1 E99. So lower end, comma, upper end. Now we put another comma. The degrees of freedom now is input as 831, and we close the parentheses. And so now this completed command will look exactly like how we completed the command earlier using the newer version of the TI-84 calculator. And so now for all versions of the TI calculators, we can hit a final enter to get our probability value. And this is the value right here. And so now on the writing board here, allow me to write down the complete command of our TCDF program. So right after the parentheses here, we put in 13.906, and then we put a comma here. 1E99 is a way to indicate indefinite upper end, and we put in the degrees of freedom being 831, and that's how we complete the command for the TCDF command. And so now the answer that we have seen, which represents this probability, or in other words, the p-value for this particular sample that we're having here. We saw earlier on the calculator it was 5.610399, and a lot longer with an E minus 40. So this way of expressing the final answer is simply just the way how the calculator is expressing, and it is, for anyone to know, it is in scientific notation, which means that we can think of that as 5.610399 and a lot longer times 10 to the negative 40. That's what the E minus 40 means when the calculator is writing it. And that means for us numerically that our answer is in 4 decimal places, which I usually round. 0.0000. And so in this lesson and throughout many of my video lessons in testing a hypothesis, I usually round final p-value to 4 decimal places. However, it is your responsibility for anyone watching this video lesson to check on the rounding requirements of your own problem. So here is our p-value, our final p-value. Now that we have found our final p-value to be in 4 decimal places, 0.0000, now we want to compare this with the significance level given in the problem. And so now let's look back at our current description of the problem of the example. So in part A, we are given significance level being 0.001 because that's what it says right here. That's what it said. At significance level, alpha equals 0.001. So that means this final p-value of ours is going to be compared directly with significance level 0.001. And direct comparison shows that our final p-value here is well below the given significance level. So now upon realizing that our p-value falls below the significance level, we come to the following conclusion. That means our d bar, the sampling difference in the two sample means as our own sample, is an unlikely sample. Which further leads to the conclusion that our d bar is, we can either say showing, or d bar itself is strong evidence. And having d bar as strong evidence here is good for us to say that we can reject, in one way saying reject h of 0. the statement that was claimed in the null hypothesis here. Or another way, logically speaking, we have D bar as strong evidence to support H1. And so now in that way, one more time back to the wording description of our problem. The problem itself is worded as a yes or no question. Are the samples showing strong evidence that this mean engineering certifying exam score of Gauss University is generally less than that of Newton University? So in that case, so now as a yes or no question, for having strong evidence or not, we are having strong evidence. And so now we can ultimately answer yes to our final question. And now as a closing remark before I'm moving out to the next question in our current example here, then again, be aware that right from the beginning, if I define, or if any of us here who is working on this problem define the two numerical labelings here the other ways around, that meaning this is population 2 and this is population 1, then this statement would have read the other way. D is less than 0, where it would become a left tail test. So again, as a reminder that anytime now that when we are doing comparing two population mean values, then testing the hypothesis as a right tail test or being as a left tail test is just generally a skill that we need to know how to handle. And that so any problem can turn into being a right tail test or a left tail test, completely dependent on how we define, how we gave our numerical label. So it's not simply because the statement in our question here has a word saying less than, then the problem has to be less than. It all depends, and it only depends on how we decide the labeling convention from the beginning. And now let's look at part B of our current example here. So all that given information is retained exactly the same here, and it's being still in the description of our example. So now part B of the example now is asking us to find a 99.8% confidence interval. So again, remind yourself that CI here means, or CI stands for confidence interval. And the purpose of our interval here is to estimate D. All right. And so now as a brief explanation of how the result we are about to do here in part B will connect with the result we have found in part A, let's quickly look at the two hypotheses from part A. From part A, alternative hypothesis was stating that D should be positive, whereas null hypothesis from part A was saying D was equal 0. And we have successfully proven that D was a positive value. We had strong evidence based on our samples. So, but that was all we had. So D bar we had was strong evidence to say that to support H1, saying that this D is positive. But in the end, we still don't know how far this D value is above 0. Is it only a small amount, like a 0.5, or a larger amount, like a 5.5, or something else? And so that's the reason why now we look at question in part B here, where we want to find a 99.8% confidence interval to really estimate D, because now we can come up with an interval with low and high, where this D value can possibly fall in between, and we will have a better picture of where our D value will fall into, rather than just simply knowing that it's a value that's falling above 0. And so now, once we've had all that understanding, then again, I need to remind anyone viewing the video or following along with this video that confidence interval at the very end will ultimately be in a form of a sample value. So it's a very powerful statement here, because sample value, when we can either have it as a given information or we can purposely find it So we will always rely on the corresponding sample value plus and minus a margin of error. And that's how the any confidence interval will look like ultimately at the end. And so since our problem here is aiming at estimating the difference of the two population mean values, D, and so the sample value corresponding to that is D bar. And we will be adding and subtracting the margin of error. And so that is how our final confidence interval will look like. And so our D bar has already been found to be 5.5. As we have already laid down all of these calculations before we even got into any of the actual question of our example. And so now from that sample value as the sampling difference of the two sample means, we can just simply find a margin of error to be added and subtract away from this sample value. And so what we mainly use now is the formula for this margin of error. I have given in the general lecture that this margin of error can be calculated by the following formula. T sub c multiply with the SEC. And once again, we have already found our SEC for the two samples right after we have sketched down the given information before we got into any of the questions. And so now it breaks down to only worry about finding this T sub c value. And recall again from our past understanding when we were finding the confidence interval, then T sub c is the t-score that's related to the confidence interval, and that's what that subscript c is all about. So let's now spend some time finding T sub c. First of all, recall that our confidence level is given to be c equals 99.8 as given from the question in the question. Find a 99.8 confidence interval. So that means our confidence level is 99.8 for confidence level. But to really use this into calculation, I am going to write that as 0.998. So now first step for calculating T sub c, we are going to go with 0.5 plus half of our confidence level. So 0.998 over 2. Calculation of mine came out to be 0.999, and we refer to this as some left area. Step 2 is to either calculate or indicate the degrees of freedom for our two samples. So now again, that same degrees of freedom we have calculated long before we got into any of the questions is here. This is the degrees of freedom for our two samples together, where 450 is for sample 1 and 400 for sample 2. So that means our degrees of freedom to be used here is 831. The last step is to now finally calculate a T sub c. So we will calculate T sub c by running a command generally known as the INVT command. And most of the times when you run this on any calculator, it doesn't have to be a TI-83 or 84. The INVT command, which is most likely looking like this as well, INVT command, will first thing ask for area left, and after that it will ask for a degrees of freedom. And usually this command is executed with the two values here with a comma between to separate the two values. So now on a TI-83 or 84 calculator, we are going to call the INVT command by accessing or pressing the key combination second variables, which will bring up all of the distribution functions in statistics. This time we will select INVT, hit enter. So this version of the TI-83, this version of the TI-84 calculator gives me a menu right here. But now for those earlier TI-84 calculators, after calling your INVT program, you may not see a menu as seen earlier, but instead you are seeing the direct INVT command being printed on your home screen right here. And now back to the TI-84 calculator that I was using earlier, where it gave me a menu after calling INVT command. For area here, I am going to enter 0.999 because that's what's indicated on the writing board earlier. I'm going to hit enter to come down to degrees of freedom. So for this, I am going to enter 831 as written on the writing board earlier. And now we're going to hit enter a few times. And so now if you have an earlier TI-84 calculators where you have to input the values manually yourself, then after the parentheses, after the opening parentheses of your INVT command being printed on screen, like what you have seen earlier, you can go ahead and type in the 0.999 as the area value and place a comma here and put in your degrees of freedom. And we close the command with a closing parentheses. And now for all versions of a TI calculator that has this INVT command, we're going to hit a final enter. And this is our T sub C value. Now I have to make a remark that TI-83 calculators do not come with an INVT program built in. And this is the reason why, in the following section of this video lesson here, I would like to show how we can run the INVT on a program that's written in Microsoft Excel. So that's in case any of my students who doesn't have a technology that runs the INVT program can have a way to calculate your T sub C value. I have also developed my own INVT program that runs on Microsoft Excel to make it convenient for students in case they don't have any calculator with them that has the functionality here. And so the box that's indicating left area is where we're going to enter 0.999. The degrees of freedom is going to be 831. And so now this is our T sub C value that I made Microsoft Excel automatically calculated for us. And so it's 3.10007, and it could be a lot longer. So as I have said earlier, unless being specified otherwise, usually for T sub C, I'll round it down to 3 decimals. But in this case, we are forced down to only a 3.1. And so now after we have found our T sub C to be 3.1, then our margin of error is ready to be completed. It's 3.1 for T sub C multiplied with the SEC that I have shown earlier, which is 0.3955. And so final calculation gave me 1.22605, and in this case I'll round it down to 2 decimals, so 1.23. Simply because usually these scores are here. Again, we're working with mean scores on engineering certifying exam, which is measured out of 100 points. So it can be equivalent to a percentage as well. And so that's why I use 2 decimal places in what I feel the best precision. But again, when anyone is working on these problems, make sure you watch for your own rounding for the final answer of a margin of error. And that now means our final confidence interval is found as following, from where our sample value being the sampling difference 5.5. We are going to add and subtract from it 1.23. And this is our confidence interval. This is the margin of error. And so the way how it says now is that guaranteed at successful level 99.8% or guarantee at 99.8% chance of successful, then the actual difference in the two population mean values is going to be somewhere up and down by 1.23 from 5.5. And again, since being a confidence interval, being an interval, we can subtract this margin of error from the center point, from the sample value in the middle, in the center, to come up with low end. So alternatively, we can write the low end to be 4.27, and the high end can be found by adding 1.23 with 5.5, which gives us 6.73. And so again, this interval, this format of the interval is referred to as the traditional format. Of the interval, because it shows a low and high. Again, at confidence level 99.8, which guarantees that successful at 99.8% chance, that this difference between the two population means will be anywhere inside of this interval between the low and the high given here. And now we are at part C of our current example. And so again, all that same sampling information remains the same. Here we are at our question C here, which is asking at significance level 0.001 are the samples showing strong evidence that mean engineering certifying exam score of Gauss University is generally other than that of Newton University. And so aside from this term other than, which is different from part A, then this question really is a repeat of problem A that we have done. So first thing to be clear again, I will stay in the same numerical labeling convention of how I started before we got into question A. And so this is how the given information is listed here on the board regarding the two samples being selected from the two populations, 1 and 2. And so from the sampling information listed here, we found for ourselves the D bar value calculated previously to be 5.5, which will be used again in this coming problem, testing a hypothesis. And we also already calculated SEC, and that will be used again in our coming problem right now. And as well as the degrees of freedom being 831 for the two samples combined together, where N1 is at 450 and N2 is at 400. And so now back in the wording of the problem, are the samples showing strong evidence that mean engineering certifying exam score of Gauss University, so mean engineering exam score of Gauss University, this is mu 2 according to our labeling convention. And so with the wording again to be continued here, we want now to say that mu 2 is generally other than that of Newton University. So that of Newton University here means the mean engineering certifying exam score of Newton University. So we want to prove now that mu 2 is other than mu 1. And so again, algebraically, this comparison statement here can be rewritten as mu 1 minus mu 2 to be other than 0. That's one way of how we can rewrite that. Or we can also rewrite the same comparison statement here as mu 2 minus mu 1 is other than 0. However, since we have learned previously that we defined D as the difference between the two population means to be mu1 minus mu2 for whichever is taking the role of number 1 and whichever is taking the role of number 2. So in that way, we are going to stay with this particular written form to make it consistent with our definition. That is D equals mu1 and mu2. And so now back to the actual question itself. And now I just once again want to point out that the question here itself is bringing up for us a testing of a hypothesis problem. Are the samples showing strong evidence that etc. and etc. And so now realizing that we're having a testing of a hypothesis problem, then the first thing is to identify our hypothesis. Our alternative hypothesis is the easier one to find. And just like what I was addressing earlier, now we're looking at D is, we're trying to say in our H1, the alternative hypothesis, D is other than 0. And now once we have had H1, then H sub 0 can be easily written as D is equal to 0. And so our problem that we're doing here will be a two-tail test. And for this example, for this part of the example, I am going to pick up the pace a little bit because as we progress through the problem, anyone viewing the video will notice that really over 90% of the structure of the problem will remain exactly the same, except for the only difference between now and what we did in part A is we switched from a right tail to now a two-tail test. So now we are getting into the steps of testing our hypotheses here. So my first step is to write down the values for D bar, which is in our case here 5.5 as listed earlier. Our SEC was calculated to be 0.3955, and the two samples came to a combined degrees of freedom being 831. So just like how I have explained in part A, if the problem here was done completely from scratch or was done completely from a fresh start here, then we would need to spend some time calculating these values before we get into any further steps. And so now upon having our D bar value listed here, SEC and the DF right here for degrees of freedom, the next step now is to calculate the T star value for our sample. So our sample is a sampling difference between the two sample means. So now T star is calculated as the difference between 5.5, our sampling difference between the two sample means, subtract 0, the value that's stated in the null hypothesis, and we're dividing that difference by 0.3955, the SEC that's listed here. And so just a reminder again that T star is the difference between our G bar value and 0, the value stated in the null hypothesis, and divide that difference by the SEC in the denominator. Calculation for our T star came out being positive 13.906. And for this problem, allow me to indeed highlight the sign of our t-score with red ink right here. So it's a positive 13.906 for our T star value. And I just now highlighted the sign of our t-score in red ink. And now after having T star value for our sample calculated, the next step is to advance to calculating our p-value. So the problem now is a two-tail, but T star itself is a positive T star. So calculating this p-value right here, I am first going to set up a probability calculation where I'm looking for a d bar among infinitely many other d bars that's greater than or equal 5.5. And so I also wrote this inequality in our probability calculation here as a right tail inequality, as an inequality that points to the right hand side, simply because this t star being positive led to using that right tail inequality, or the greater than or equal inequality here, which is the way how we can decide the inequality in our p-value calculation anytime doing a two-tail test. And further, as I have addressed, our test here is being a two-tail test. But this probability calculation here is only a right tail probability calculation. So we need to multiply this overall probability by 2 in order to ensure our final p-value. And so we can think of this right tail probability as the area on the bell curve. So we now want to be aware we have a bell curve where any of our sample d bar right here can be placed on this line right here of the bell curve. Center of this bell curve is 0, and this is where we can find all values of d bar. So this particular value 5.5 is somewhere to the right hand side on this of the bell curve center. So d bar that we have is 5.5, and this d bar is at t star score being 13.906. So again, back to what I was in the middle of saying, this probability calculation that I underlined with the brackets here can be understood as the area shaded to the right hand side of 5.5 on this bell curve. And in that way, the final p-value where we double this probability can be understood as doubling of this amount of area. That means we can imagine there's another area exactly symmetric to the area that we have drawn earlier, but pointed to the left-hand side. And so our final p-value is understood as the total of these two areas combined. But so in order to calculate this area, before we can double that, we need to run our TCDF command. Or generally speaking, we need to use some technology to help us calculating this area. So TCDF command is a calculator command that I'm using on the TI-83 or 84 calculator. And this command only runs with t-score value, and this is the reason why we have to calculate our t-score value for the sample that we're currently having. So now on my calculator here, which is a TI-84 calculator, we are going to call the TCDF command by pressing the key combination second variables, which will bring up all of the distribution functions for statistics. And so now we're going to scroll down and look for TCDF command and hit enter to select that command. TI-83 calculators and some earlier TI-84 calculators, after calling the TCDF command, it will print the command directly on your home screen as currently seen here. And so now back to the TI-84 calculator version that I am currently using, where it shows a menu after we call the TCDF command. This lower end right here. Now back on the board, our shaded area here, as indicated here, has a lower end being at t-score 13.906. So this is going to be the t-score we provide to the TCDF command as lower end. So on the calculator, 13.906. As you have already seen earlier, the interval that we're looking at does not have a definite upper end. So we'll have to leave that 1E99 to indicate this is indefinite upper end. the degrees of freedom for the two samples here combined came to 831, and that's what I input that here. So now I'm going to hit enter a few more times after successfully completed all information that the calculator asked for. So some words for the TI-83 or early TI-84 calculator users here. So if your command is being printed on screen, just like what you're seeing here, then you have to type in the lower end with a comma, the upper end with a comma, and with the degrees of freedom, and close the parentheses here in order to run your command. But so now at this point right here, after we have successfully completed our command on any TI calculator, we're just simply going to hit a final enter. And this is our probability, or the area that is right hand side on this bell curve here, to the right hand side of 5.5. So allow me a minute here to complete the command of this TCDF command right here. So we have 13.906. We put a comma here, and that was low end. 1E99 is for the indefinite upper end, and our degrees of freedom being 831 as stated here. And so this is the answer to how big that area is. But now do not forget, we need to eventually double this probability to achieve our final overall p-value. The answer from the calculator gave us this quantity here being 5.6103 and a lot longer, but with an E minus 40. This numerical expression here means our answer for that small area here. One side is simply 5.6103 and a lot longer times 10 to the minus 40. So this is the way how a lot of calculators are indicating scientific notation like that. But then don't forget, our answer needs to be multiplied with 2. So we multiply each of these values by 2. The lengthy scientific notation here truly means in decimal. And usually for my lecture, I round my final p-value to 4. I round my value to 4 decimal places. And so with a value like this, after multiplying by 2, our final answer in 2 decimal places should be just simply 0.000. So now that we have had our final p-value, the next step is to compare this final calculated p-value with the significance level. So back on our lecture notes here, back on our computer screen here, then we had significance level given at what's indicated here, alpha equals 0.001. So in that way, we are going to compare our final calculated p-value with the significance level given as 0.001. And now direct comparison shows that our p-value falls well below the significance level. And so now having our p-value falling below the significance level leads to our conclusion that d bar as our sample, being the difference in the two sample means here, is an unlikely sample. And being an unlikely sample further leads to the conclusion that our d bar is, or our sample as a d bar is showing, or you can just simply say is itself strong evidence. And the evidence here is in one way to reject H sub 0, the statement that's claimed that D equals 0, the null hypothesis. Or in another way, we can say that D bar is our strong evidence for us to support H1. And ultimately, as a yes or no question, as stated here, are the samples showing strong evidence? We here now just verified that we've had strong evidence from our sample value. Then ultimately the final answer for to this question is yes.